Welcome to today's webinar titled Galileo High Accuracy Service Tests in Different Operational Conditions, based on a paper published in the winter 2024 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Dr. Chiro Joya. Dr. Joya received an MS in Nautical Sciences and a PhD in Topography and Geomatics from Parthenope University in 2009 and 2014, respectively. Since 2013, he has been working at the Joint Research Center of the European Commission, providing scientific support to policymakers in the development of EU space policy. Currently, he is the project officer at the Galileo sector of the JRC. His research interests are primarily centered around location and navigation, with a particular emphasis on the applications and advancements in GNSS. He explores the integration of GNSS technologies with geomatics to enhance positioning accuracy, reliability, and performance in various environments. His work delves into the development of robust GNSS solutions that address challenges such as signal interference with multipath effects, which are critical for improving navigation systems used in transportation, aviation, and emergency response. Today's webinar is being recorded and will be available on our website and YouTube. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will now turn the time over to Dr. Joya.
Okay, so thank you for the introduction. I hope you can hear me well and you can see also my presentation. So today for half an hour, I will present you the results of our work on Galileo High Accuracy Service tests in different operational conditions. Before starting the technical presentation, I would like to spend a couple of words on the environment where I work. I work for the Joint Research Center of the European Commission, and we provide scientific and technical support to the European Commission and also to the USPA in order to develop Galileo. And I work in the Galileo sector at the GRC, and here in the picture you can see the current member of our group. Our group is built around our lab facility, which is the core of our activities. And then around we have a group of around 15 people working in the lab, but also on different type of activities. If you would like to have additional information about our testing capabilities, you can download the document shown in the slides, which report all our facilities. So now I can really start with my presentation. So the presentation is composed by 5 blocks. At the beginning, I will present briefly Galileo Accuracy Service. Then I will try to show you the research questions that we will try to answer during this presentation. I will show the methodology that we have used to answer this research question. And then I will try to summarize some of the key messages that we can bring home. Finally, I will have just 1 minute to conclude my presentation with some new activities we are carrying out at the GRC. So the Galileo High Accuracy Service is the new service of Galileo. It has been developed because there is a growing demand for high accuracy locations. Users are getting used to high accuracies. They are asking more and more accurate position solution, starting from the automotive sector, where the autonomous driving is a key users of this type of services, but also moving to survey and geomatic applications, and finally also to personal navigations. All these applications are requiring high accuracy positioning, and the classical method, the single point positioning method, does not enable this type of accuracy. So different methods should be used to reach decimeter level of accuracy. There are different methods that can reach this type of accuracy, moving from the single point to the more complex RTK approach. But in the recent years, the PVP is gaining a lot of space in this framework. And Galileo High Accuracy Service is a key enabler for PPP worldwide. The service is free of charge, and Galileo provides correction through signal in space and internet connection. These correction will currently are enabling decimeter level positioning accuracy. And so, briefly, the story of the Galileo High Accuracy Service. Currently, we are in phase one, but it started in phase zero with the testing and experimentation. The phase one, so the initial phase of the service, has been declared in January 2023. The phase two will come soon with additional correction, in addition to the current correction of orbit, clock, and bias correction. It will be provided also ionospheric corrections. There are two service levels within the Galileo High Accuracy Service. The service level 1, which has a global coverage and an accuracy of horizontal and vertical accuracy of 20 centimeters, with a convergence time of about 300 seconds. The service level 2, exploiting the regional ionospheric correction, will have almost the same accuracies, but the convergence time will be reduced, passing from 300 to 100 seconds. Galileo High Accuracy Service is not new. It attracted a large interest from the manufacturer, but from the industry, but also from the research point of view. There has been several papers analyzing the infrastructure of the service, the correction availability, and the accuracy of the correction provided. Finally, also in the position domain, there have been several studies analyzing the positioning accuracy achievable using the accuracy service correction. This large interest has been verified and can be demonstrated counting the number of papers presenting to the ION conferences, but also to other navigation conferences all over the world. But in our studies, we focused in the results in dynamic condition, including challenging environmental condition in the presence of multipath, for examples, which is a common error for one of the target application of high accuracy service, which is the automotive domain. And then we will also evaluate the high accuracy service prototype developed under two different projects, one founded by the European Commission and the other one founded by EUSPA. So in this study, we have four basic research questions. The first one is, what are the benefits in the PVT domain of the application of high accuracy corrections with respect to the usage of only the broadcast navigation message? Then we will analyze if there is any impact of the reception conditions. So if in an urban environment, there is a clear impact on the availability of the HAS corrections. And we will also measure the accuracy achievable in PPP mode in this type of environment. Then we will also evaluate the impact in case of a dynamic receivers. For example, we will do some tests using our van. And finally, the last question is how the high accuracy service prototype developed under the two different projects will perform compared against the standard PPP algorithm. So the metric used to perform our analysis are the metrics typically used to evaluate PPP algorithm. So we use the horizontal and vertical accuracy, and to measure this, the accuracy, we use the 68th percentile of the error after the convergence time. Then we evaluated the solution availability, defined as the percentage of the time during which a PVT solution can be computed. Then finally, as you remember from the research question, we analyzed also the high accuracy service message availability, which in this study is defined as the percentage of time in which the high accuracy service correction are available without considering the validity of the corrections. And finally, we will try to have also an evaluation on the convergence time. In this case, we have only a limited number of tests, so it is not a statistical evaluation of the convergence time, but it is the convergence time measured in a specific test. And in this case, we define convergence time as the time needed to reach the target accuracy. So, how we are going to answer to these questions? We have four different receivers. In this slide, you can see green and orange boxes. The green boxes represents the boxes related to the two high accuracy service prototypes that I was mentioning before, while the orange boxes represents the methodology developed to analyze the impact of high accuracy service correction using commercial off-the-shelf receivers. In this case, we consider two different receivers. The first one is the septentriopolar RX5 receivers, which is a high-end receiver. But on the other hand, we have also a low-cost receiver, represented in this test by the U-Blocks F9P. For the two prototype receivers, the methodology is quite simple because we have directly taken the output provided by the two devices, and we compared this output against the reference solution, computing the positioning errors. While for the commercial off-the-shelf receivers, a different methodology has been used. We collected the RINEX data from the two devices in order to collect the observables of the devices. Then we used the navigation message provided by the broadcast navigation message, and we collected the high accuracy service correction from the signal in space. In order to parse this correction, we have used HasLib, which is a software developed under a EU-funded project. So using these three input, we have used as navigation engine RTKlib settings, RTKlib with specific settings. And I will show you how to set RTKlib. So in these slides, you can see the settings that we have used for this type of test. But I would like to stop here just for a couple of minutes to properly show you how we implemented these settings. So I will show you now an example with a short dataset on and how we implemented this methodology. So I'm going now to share you my screen. Okay. You should see now my screen in which I have in the upper part the RTKlib software, and in the lower part I prepared a dataset that we can analyze right now. So instead of analyzing the settings as shown in the slide, here is the name of the file containing the observation. Then we have the RINEX navigation message, and here we have the high accuracy service correction provided in RTCM3 formats. Finally, we can set the name of the solution that we are going to compute, but we have another windows in which we have to set the parameters of our PPP solutions. For these studies, we have considered the PPP solution in kinematic mode. We have considered all the possible frequencies, the forward filter, and the elevation mask, for example, is set to 10 degree, but it is fundamental to understand that we are going to estimate the ionosphere, so we are not going to use iono-free combinations. We are going to estimate also the tropospheric correction, and this is the fundamental element. We are combining broadcast correction plus SSR corrections. Then you can play with the different configuration, having almost an infinite number of possible combination of the PPP, but these are the configuration that we have used for our study. So we have enabled in RAIM-FD algorithm in order to detect and reject outliers. We enabled the phase wind up, and we consider GPS plus Galileo. So we can now finally move to the processing. If we run this example, we will have the results in about 30 seconds. It's just the time of the software takes to read and process the observables. We can see here that the RTK software is showing us that the solution type is 6. This number represents the fact that the solution is processed in PPP mode. And then we can see the results of this processing comparing the different type of solution. Just for clarity, I have already processed the solution in different other modalities. In this way, we can directly compare the solution obtained now with the settings that we have put in the software with the previous solution computed with the different settings. Obviously, for our study, we did a different approach because we didn't we processed just the data with the RTKlib, but then all the analysis were done in post-processing, importing the results of RTKlib in MATLAB scripts and analyzing the results with respect to the reference trajectory. So the software is almost finishing, just a couple of seconds, and it will finish the processing. In this case, I'm using 1 hour of data at 1 hertz data, so with 1 second data rates. And here it is important to note that the high accuracy service correction were taken from the antenna placed on our lab, which is connected to a receiver which is logging 24/7 CNAV message. So we have a continuous log of the high accuracy service correction also for monitoring purposes. So the software is almost finishing the processing, and now we can finally plot the results. Just 1 second. Okay. And here you can see clearly the solution obtained using these data sets. And if we want, we can even compare this solution opening and a solution that, for example, I have processed before. In this case, for example, if we want, we can compare the solution against a solution obtained with the same PPP settings, but considering only GPS. We can see here that there is a clear advantages of moving from the single to the multi-constellation case because the green line is more smoothed than the purple line. So with this, I just conclude the demonstration of the methodologies, and I will go back to my presentation. Just give me the time of going back to this. So with this, I conclude the methodology part of my presentation, and we can now move to the setup. I I was promising you the analysis in different type of scenarios and different conditions. So we started from the easiest way. So in static conditions, we have two different scenarios. One in open sky condition, in which the antenna is placed on the tallest building in the area. So it is in open sky condition. There are no obstructions, and it is represented by the blue marker in the slides, while another scenario was in the degraded scenarios. In this case, the antenna is placed just outside the buildings, with a building which is tall and is almost 30-meter height. Around, there is another reflecting building on this side, but this was not enough because we have also a tree here introducing further attenuation on GNSS signals. So the signal degraded scenario in this case is very challenging for the GNSS processing. So a preliminary analysis comparing the data in the two different type of scenarios. We can see here the number of visible satellites for the two cases. In the open sky condition, we can see that the number of GPS satellites varies between 10 and 12, while for Galileo it varies between 7 and 10, but it's almost constant. The situation is completely different if we analyzed the obstructed scenarios. In this case, there is a reduced number of satellites, and in addition, there is a clear fast variation of the visible satellites. This can be clearly seen also in the geometric domain. In this case, the yellow and purple line represent the north and east dilution of precision for the open sky conditions. And we can note that the north dilution of precision is higher than the east case, as this is due to the constellation design. But the situation is completely different for the obstructed case. There is a fast variation of the dilution of precision, and in addition, we can see that the east value of the DOP is higher than the north DOP, showing that there is a clear masking of the building in this type of scenario. But the geometry is part of the story. Let's have a look also to the quality of the data. In these slides, I show you the time evolution of the multipath linear combination of the two different scenarios. We can note that in open sky condition, the standard deviation of the multipath linear combination was about 26 centimeter, while in the obstructed scenarios, this value is about times higher. So there is a significant multipath in the obstructed scenarios, as you can see from these slides. But we moved also from the static to dynamic condition, as I was mentioning before, because the automotive is a key market for high accuracy service. We did several tests, and in this study, I present you the test performed in Milano using one of our van in the city centers with a moderate to heavy urban scenarios. The antenna was placed on top of the van, and it was connected through a splitter to four different receiver types. The test duration was about 40 minutes, and the conditions were typical of automotive environment, with continuous start and stop, with part of obstructed sky, as can be seen from the figure in the slides. So for this test, it is fundamental to estimate properly a reference trajectory. We have a different type of reference trajectory depending on of the needs. Because, for example, for the static test in open sky condition, we have high accuracy post-processing kinematic capabilities. So we collect long data collections and we process them in RTK mode, having millimeter level accuracies. But this approach was not suitable for the signal degraded condition. For this type of condition, we have used the total station, which is a topographical instrument giving us centimeter level accuracy also in this type of solution. But obviously, the total station was not suitable for the urban scenarios in the van. And in this case, we have used a GNSS plus IMU high-grade devices with post-processing capabilities, reaching also in this case centimeter level accuracy. So we can finally move to the analysis of the results. We have seen the graph on the right side, on the left side of the slides, I think a lot of times, but I cannot avoid to put it here. In this case, we are analyzing the performance of the two prototypes developed under the two different projects, and we have three different markers. The blue one, which are the marker related to single point positioning, while the yellow and the orange marker represented the PPP solution provided by the two devices. It's clear that there is a clear advantages moving from single point to PPP solutions, because in the PPP case we used also the carrier phase measurement, and we have a filter which clearly smooth the errors. If we look at the results on the right side, the results using the two commercial off-the-shelf devices are reported. And in this case, we are going to analyze the impact of using high accuracy service correction. Because if we compare, for example, the green market with the purple market, that represent the solution provided by the septentrion receiver with and without the accuracy service, we can see that the 68th percentile of circle is smaller because there is a clear reduction of the error using the accuracy service correction. We can analyze also the time evolution of the horizontal error. In this case, we can note that there is a transient for all the type of solutions, which this transient varies between 28 minutes for one of the two prototypes, to up for 3 hours for the case of the U-blocks receivers without using high accuracy service. But we can also note that all the solutions were able to reach the 20 centimeter benchmark. And we can note that the errors remain stable below the 20 centimeter after the convergence. But we can also note that there is a clear reduction of the convergence time when using the high accuracy service corrections. If we analyze the statistical value of the horizontal and vertical errors, we can clearly see that there is a significant improvement moving from the PPP to the from single point to PPP, and this is obvious. But we can also note that the high accuracy service prototypes have performance in the order of 7-8 centimeter for the horizontal channel and 10 centimeter for the vertical one. Analyzing the impact of the usage of the high accuracy service correction, we can see that there is a clear error reduction when we use the high accuracy service correction for both type of devices. So for both the high-end receiver, but also for in the case of the low-cost devices. And the improvement is also clearly visible if we consider the convergence times that moves to hours to less than 1 hour for the two type of devices. So we can move to the more challenging scenarios. In this case, it was not clearly possible to identify a convergence of all the solutions. So I am showing you here the results of the whole data sets. And we can clearly see that the error is generally reduced using the accuracy service correction, but there is a clear jump of the error even after the convergence. So even if the error was reaching low values, the presence of local effects such as the multipath can clearly degrade the solution of the different devices. You can see from the sky plot that there was local multipath even to high elevation satellites, which clearly affected the PPP solutions. So we analyzed the error along the three different components. Starting from the north, we can note that the two devices, the two prototypes, have a performance similar to the U-blocks devices, applying the high accuracy service corrections. But for the east component, the situation is different because in this case, the U-blocks devices using the accuracy service correction has the smaller errors, similar to one of the two prototypes. For the vertical component, the two prototypes and the septentrions have very similar performance, while the U-blocks in this case has very large errors. And we can also confirm in this case that the local multipath and the obstruction of the sky create convergence issue for all the type of devices. So we can move finally to the most challenging scenarios in dynamic condition in urban environment. Let's start with the analysis of the correction of availabilities. Here you can see the trajectory followed by the van, and we color coded the trajectory with the multipath linear combination in order to show you that there are areas in the city in which the multipath is more severe. But you can see also yellow square and red square. The yellow square represents the point in which the device was not able to retrieve high accuracy service clock correction, while the red squared box represent the point in which the device was not able to retrieve the Haas orbit and code corrections. And we measured that the real-time correction availability for this test was about 95% for both type of corrections. Hence, we cannot see a clear effect of the environment, and we can note that Haas correction availability is barely affected by these challenging conditions, also thanks to the fact of using the validity of the corrections. I here show you the results of one of the two prototype implementing already the PPP solution with high accuracy service correction, but the other devices has very similar performance. We can see that in many environments we were able to reach the 20 centimeter target of the service, but we can also note that there are gaps in the solution due to the presence of tunnels and also to the presence of very narrow streets. But we can also note that there are areas in which the error is quite large, and this area corresponds to the area in which the multipath linear combination was larger, showing again that the presence of local multipath can severely degrade the PPP solutions. So here I summarize the performance of the different configuration analyzed in dynamic conditions. We can note that all the PPP solution can provide a significant gain in position accuracy if compared to the single point solution. So even if there are several severe degradation of the code and carrier phase measurements, it's still good to move from single point to PPP solution to increase the accuracy. But we have also to consider the solution availability for the different devices. Because for the high accuracy service user terminal and the PolarX, we have slightly larger error on the vertical component, but a slightly higher availability. While for the other prototype, we have higher accuracy, but a lower availability of the solution. So let me just conclude this presentation with some key messages that we can bring home. So we are going to analyze what are the benefits in the PVT domain of the high accuracy corrections against the use of the only broadcast navigation message. We have seen that the benefit of the high accuracy correction is clearly visible, and there is an error reduction and a reduction also of the convergence time in all the different scenarios that we have considered. We analyzed the impact of the reception condition and of the receiver dynamic on the availability of the correction. And we have seen that there is in urban environment in dynamic condition, the correction were available for about 95% of the time, also in this type of condition. But the presence of multipath and cycle sleep on the carrier phase could determine large error in the PPP solutions. Finally, we have analyzed the performance of the high accuracy service prototype developed against standard PPP algorithm using the high accuracy service corrections. We can say that a clear comparison is unfair because we don't know the internal processing logics of the two devices, so we don't know when the devices is clearly outputting the solutions. So the comparison should be only performed if we consider an intersection of the same epochs. So with this, I just conclude my presentation, and if you have any question, you can start reading our paper available on the website. But give me just 1 minute to present our ongoing activity, because starting from our paper, we have implemented different strategies. In order to monitor the correction quality, so we have developed a HIS CQM module, which is continuously logging the data, parsing the data, and we are analyzing the error in the orbit and clock domain for the satellites against IGS products. But we are also analyzing the high accuracy service performance in the PPP domains. We have developed our internal algorithm, which is called June, and this is the GRC user navigation engine, which allows to us to implement properly high accuracy service correction application and to monitor the performance in the PPP domain. With this, I just have really concluded my presentation, and thank you for your attention.
Thank you, Dr. Joya, for this great presentation today. We had a lot of attendees, which is great. We're now going to accept questions from the audience, so we're going to switch into Q&A. As a reminder, you can submit your questions using the Q&A button down below in your viewer. We already have questions rolling in, so we can just go ahead and jump into these. Let me take a look here. Okay, first question is there any plan in HAS to provide the uncertainty of satellite corrections as part of the message, even if it's not currently supported in, for example, IGS compact SSRI format, sorry, SSR format?
Yes, there is a plan also to provide this type of information. These information are still under discussion at the European Commission level. So I can tell you that the plan is there. I cannot tell you in which format and in which time frame it will be available.
They also have a follow-up question here, which is any plan in HAS to provide Earth rotation parameters information, which are currently only accessible in GPS and not in Galileo?
Yes, also in this case, the parameter are under discussion for the provision of this type of a parameter in the phase 2 of the high accuracy service correction. And I can fully understand that there are some applications that can really use this type of informations. We are trying to encapsulate this information in the phase 2 of the high accuracy service.
Thank you. Okay, next question is, what is the expected improvement in accuracy for users who apply HAS corrections?
Okay, so the expected improvement for the user can vary. We saw the different results in the different scenarios. What I can tell you that there are targets for the PPP solution provided using high accuracy service correction, which are 20 and 40 centimeters, 95 percentile of the time. Obviously in open sky condition, this can be verified. Then if we move around the city and the geometric condition varies and we have different type of error affecting our solution, it's quite difficult to give you an overall answer or an overall number or to this question. So I can tell you that we have seen for example, from our study that in all the type of scenarios, there is an improvement with respect to the use of only navigation message, because in any case we have a reduction of the orbit and clock correction of the satellites. But if we move in an environment where there are other dominant errors, this could mask the benefit of the AS corrections. So overall, we have a clear advantage and benefit in open sky conditions, but also in all the type of scenarios. But to tell you if it's 10 centimeter or 20 or alpha meter, it's difficult.
Okay, next question. Did you do any modifications to the RTK LIB source code, or did you use it as is?
No, we used as it was at that time. So we use RTKlib in that. If you want, I can tell you the release. It was 2.4.3, and we used that release of RTKlib without any type of modification.
Is there a timeline for phase 2?
I cannot disclose this type of information now, so we can move to the next question.
Okay. Are there any discussions for using this service in aviation with ICAO aircraft manufacturers?
I think that the use of the PPP solution for aviation is quite challenging due to the fact that we need to have a bounding, and this could create a lot of discussions. So bounding with the Kalman filter is quite challenging. This could limit, at least in short term, the adoption of this type of correction for aviation purposes. But in any case, if if the users is going to use single point positioning, it already can refine its solution applying the high accuracy service corrections. So not going for a full PPP solutions, but refining the single point positioning solution with additional corrections.
Are there any alternatives in terms of software and methodologies to evaluate the impact of HAS correction on the PPP solution?
Good question. So, it depends on which software you are going to use. I can fully understand that not all the software developed for the research purposes are able to read RTCM formats. And this is the reason why we moved towards RTKlib, because it was a software able to op- open and able to process RTCM solutions. But alternatives are there because, for example, uh, um, if you have your own PPP software able to fully able to retrieve the navigation data and apply the correction, it's fine. But you can move using haslib, for example, decoding the correction and putting them in another format. Or there is another software that has been developed at the GRC for the decoding of the correction, which provide you the correction in different Excel files or CSV files, so in which you can easily load it in your software. Or we are developing currently a solution which is to merge the broadcast information together with has correction, providing as output the satellite position and the clock and the bias information in SP3 clock MBA format. In this way, typical PPP software will be able to measure the impact of using refined orbit coming from has correction without large modification of the software.
Okay, next question we have here is, can you please explain the transmission of HAS correction in real time?
Okay, so the AS correction are broadcast through the CIS signals, and there is a scheme for the decoding of the corrections, and the description of the message, including the high accuracy service correction, is available in the ICD. If you want to know what are the correction that has is providing currently, it is providing orbit correction um, and code bias corrections, and finally clock correction for the satellites. This will allow the user to get a more refined position for the satellites and a refined clock solution for the satellites. In addition, you will have to apply the code correction for the different frequency you are using. I hope that this is more clear now.
Thank you. Okay, we still have quite a few questions, but if we're good on time, we can keep going through them.
Yeah.
Okay, next question we have here is, do you monitor and provide model data for ionospheric and tropospheric errors as an augmentation to receiver estimation techniques?
As a JRC, we are not monitoring and providing this type of information, but ionospheric information will be provided in the second phase of Galileo High Accuracy Service. And uh, I am not sure about troposphere. I don't think that this will be this information will be provided. No, I'm quite sure that they will not be provided. But for sure, the user of phase 2 will have information related to the ionosphere, at least in European area, because the service level 2 is foreseen with a coverage area which is almost over Europe.
Okay, what are the challenges for users and developers in accessing and integrating Galileo has into existing systems and devices?
Okay, so for accessing the Galileo has data, you have two ways. The first one is going through the signaling space. And for this solution, you need to have E6 capable receiver and E6 antenna. So in this case, you need to receive the signaling space through E6 data, decode it, and then applying the corrections. While, on the other hand, Galileo High Accuracy Service is providing correction also through the internet. In this case, you need to set up your internet connections, receiving the correction from the GSC, taking the RTCM correction, decoding, and then applying it to your PPP solution. Also, in this case, which is the best solutions? They are totally equivalent. Um, and then it depends on the user needs. For sure, for a mobile phone user, it will be easier to connect through the internet and getting the correction over the internet than implementing all the E6 tracking and decoding of the navigation message. But it depends from the user point of view. You have these two ways of retrieving the data and applying them in a PPP solution.
Thank you. Let's do, let me see here. Let's do one final question. I know that there are still some questions rolling in, but Dr. Joya, if it's okay with you, people can
Okay.
contact you at your email
Yeah, for
address.
sure. Yeah. No problem.
Okay. So let's go ahead and do this last one here. Have you, oh, let me take a look here. With the further development of HAS, could it be used for CM level high precision surveying applications?
Yeah, for sure, the development of HAS will be in the provision of the ionospheric corrections, but also in code bias that I hope it will come, the carrier phase bias that I hope it will come soon. And I think these two elements will definitely help also in survey applications.
Okay, well, thank you everyone for joining us for today's webinar, and thank you, Dr. Joya, for your presentation. It has been very well attended and lots of participation today. We want to remind everyone that a recording of the webinar will be posted to our website and YouTube, and then updates on our social media channels as well. And these will be posted by Friday, the 28th. So thank you again, and we look forward to having everyone back for a future ION webinar. Our next webinar will be on Monday, April 21st. So we hope to see you then. Thank you, everybody.
Thank you too. Bye bye.
Thanks. Bye.